Hello, today we're going to be taking a closer look at the Higgs boson, which is commonly known as the God particle. And now this is a theoretical particle that people at CERN, which is a research facility in Switzerland, have been looking closely at for several years, a project that started in the 1980s and had just come to a conclusion on July 4th in 2012. So the Higgs boson is a really huge important particle that's important in particle physics. So particle physics is a section of physics that is used to understand our universe by looking at the fundamental elements that make up the universe. So one of the main theories in particle physics is the Standard Model. As you can see from the Standard Model right here on the screen, it's made up of quarks and leptons. Now, within these sections of quarks and leptons, there are things that you may recognize. The electron is part of a lepton, and then the quarks are made up of all these 6 different types of quarks: up, down, charm, strange, top, and bottom. And protons and neutrons are made up of several quarks, and there's also the electrons within the leptons. So these are just the smaller fundamental elements of things such as protons, neutrons, electrons, those common particles that we know in our atomic world. Each of these quarks and leptons, so within the Standard Model, there's the quarks and leptons, 6 in each section. There's also 4 major forces. There's electromagnetic force, gravity, weak, and strong. Now, each of these forces it relies on a boson, something called a boson, to allow these to happen. For example, the electromagnetic force requires the use of the photon boson in order to create that electromagnetic force. The gluon is responsible for the strong force, and the W and Z bosons are responsible for the weak force. Now, that weak force is something you may have never heard of before, but it's actually very important. There's these little things called neutrinos, which are in the lepton section, which are emitted from the sun. And actually something very cool is if in every square inch of your body at any given moment, there are 60 billion neutrinos zooming through your body at that 1 square inch at any given time, emitted from the sun. So a good reference of that is if you look at your thumbnail. In your thumbnail, at any given point in the day, there are 60 billion neutrinos zooming through. So that's just something really cool. So anyway, all of those forces require a boson. Now, that's where the Higgs boson comes in. According to the Standard Model, based on this Standard Model that is so vital and fundamental to how we understand physics today, there's nothing that explains how objects in our world acquire a mass. So that's why a scientist with the last name Higgs named the Higgs boson after himself to describe where objects get mass from. So that's what gets us to prediction of the Higgs boson and what it all means. Well, the Higgs boson is a particle that's responsible for giving mass to other particles. So a way to describe the Higgs boson is, if you think about, it's basically a giant force field. What Higgs theorized is that there's a giant force field called the Higgs field in our universe that started from the very beginning of time, that is essentially everything that has mass interacts with this field. So a great analogy for this is the cocktail party analogy. So let's say that you're at a cocktail party and the room is really full of people. Someone opens the door to come into the party, and it's just a regular commoner guy, just kind of not important guy. He just is coming into the party. That guy can walk through the party without talking to anyone, without causing a commotion. It's almost as if he's weightless. He's just easily passing through the party. Well, now let's say that someone comes in, and it's someone very important, maybe President Obama. Well, everyone in the cocktail party is going to surround him. Maybe paparazzi starts taking pictures, trying to get autographs, trying to talk, and he's bogged down by all this weight of the people. So the cocktail party room with all the people is the Higgs field. And so the Higgs boson kind of has this almighty power, okay, the God particle, to choose which particles in our universe get to have mass. For example, photons and light rays, electromagnetic fields, all of that, no mass because they're not interacting with the Higgs boson. But things like protons, neutrons, electrons, the things that make up our everyday items in our life, they are constantly interacting with the Higgs boson field and having mass, and that's why things have mass. So, at CERN in Switzerland, Geneva, Switzerland, there's a huge research facility, and they built this giant machine called the Large Hadron Collider to test this theory. It's essentially a 17-mile loop of tubing deep underground where they take particles and collide them together in order to prove the existence of this Higgs boson. Well, what they're doing here is they're basically trying to recreate the conditions that were present 1/billionth of a second after the creation of the universe. So they're really trying to recreate the Big Bang. And what they're doing is they're taking a proton from the nucleus of a hydrogen atom and putting it into the machine and then feeding more protons into the Hadron Collider. And they're using magnets to adjust the path of these protons so that they will directly hit and collide with each other within 4 locations along the 17-mile ring that will then collect that data, send it a ton of data into the computer systems, and thousands of scientists will then sift through that data in order to figure out if this Higgs boson really does exist. So, in order to do this, the magnets within the Large Hadron Collider have to be at an incredibly low temperature of negative 271.3 degrees Celsius. This is colder than outer space. And in order to cool those, they have to use liquid helium, which is very difficult to manufacture and takes another bunch of scientists at CERN. So it's a huge project. It's been going on for several years. And then the protons that are circulating throughout the 17-mile ring, they're traveling at a speed 99.999% the speed of light. So they can go 11,000 times a second around the 17-mile ring of the Large Hadron Collider. It's just incredible. It's an incredible piece of machinery, and actually getting these particles to collide at exactly the right moment within the 4 stations located around the piece of machinery is like taking 2 needles and firing them at each other from a distance of 10 kilometers away and having them meet exactly at the tips of their needles, exactly midway point through their travel. So it's very difficult and very precise, and a lot was riding on this. Well, on July 4th, 2012, they turned the machine on, sift through all the data, and actually discovered a particle that they're titling Higgs-like. So they haven't 100% confirmed that the Higgs boson does exist, but they found a particle that exactly matches what they predicted and matched the theory. So they're pretty sure that it does exist. So it was a huge celebration and a great day for science. And so I just have a quick video explanation of what goes on inside the Large Hadron Collider, which we'll watch.
The Large Hadron Collider is the most powerful particle smasher ever built. In several stages, it accelerates protons to an energy of 3.5 trillion electron volts, and when it reaches full power in 2014, will whip them up to 7 trillion electron volts. The process begins when a proton is broken out of hydrogen gas. A linear accelerator uses electric fields to send that proton on its way. Then, the proton synchrotron booster uses magnetic fields to steer the proton into a circle, and electric fields to add energy. After that, the proton enters a larger ring, the proton synchrotron, and then an even larger one, the super proton synchrotron. Meanwhile, other protons go through the same process. Finally, they are fed into the main collider ring. Protons circulate in side-by-side pipelines in opposite directions. When physicists flip the switch, magnets steer protons to cross paths inside one of the instruments, and some of them collide. Here we
Alright, so that was just a really quick explanation of what goes on inside of the Large Hadron Collider. So the next question is, almost $8 billion went into this project of building the Large Hadron Collider. So a lot of politicians and just people in general are asking, what are the next steps for CERN? Well, as far as particle physics go, it's an incredibly amazing piece of machinery that we have in our hands now to look at the universe and how we're created and what makes up the world that we live in. So they're going to be scientists right now. Currently, the Large Hadron Collider is closed for renovations, and they're changing things up because a lot of scientists at CERN are working on writing up new experiments that they can do to further investigate the Higgs boson. They're also going to be looking at things such as dark matter, black holes, anything that creates, anything in particle physics. They're going to look at things. What about more particles that may have existed since the beginning of time that we don't yet know about? We have this wonderful piece of machinery that can help us learn more about the world that we live in, and it's so incredible and a really great step for science. So that's what they're working on at CERN, and that's the future of science. So thank you very much for listening.